Good morning. Today we're going to talk about crosshole sonic logging, focusing on how it works and what it can and what it cannot do. Drilled shafts or bored piles can suffer serious integrity issues from a variety of issues. Professor Mike O'Neill, who's since passed away, wrote a very nice paper, the reference that you can see at the bottom of the screen, showing various construction-related causes for integrity problems, problems that are caused by casing installations, problems that are caused by the introduction of slurry and the way it is handled. Since drilled shafts have generally high loads, they have relatively little or no redundancy. Therefore, the integrity of each shaft is critical. Sonic logging in the United States is very frequently specified to detect defects on drilled shaft construction. In this particular case, there's a study that shows that two studies, one in southeast United States and one in the middle of the United States. The locations of defects basically concentrated near the top of the pile, which is critical because that's where all the loads are transferred into the shaft. Some at the bottom of the pile, a good portion. Those may or may not be very serious because many shafts are designed for shaft resistance only and no end bearing. and a fair percentage of problems in the middle section of the shaft. And the percentages of shafts that had an anomaly were relatively high. Over 1/3 of all the shafts had some type of an anomaly. Now, an anomaly is something in the crosshole sonic logging test that looks unusual. It doesn't necessarily mean that it's a defect. The typical drilled shaft inspection in a dry cast shaft is generally good enough for a visual inspection. You can look down the hole. In the wet cast, where you're using bentonite or polymer slurry, visual inspection is impossible. So some non-destructive testing is needed, and the options will include low-strain integrity testing, PIT, pile integrity testing. It's a pulse echo method. It has a ASTM designation standard D5 882, crosshole sonic logging, which is the focus of this lecture, ASTM D6760, and thermal profiling, which has an ASTM D7949. So how does it work? There's a very nice recently published study in Russia which shows a numerical simulation of the crosshole sonic logging event. Let's imagine we have a perfect pile with just two access tubes. And if we generate a signal on the A location in the shaft and propagate it across the pile to the B location, we can see that the spreading of the wave with time. On the left, we have shortly after the pulse has been generated, and the pulse is radially symmetric. And with a little bit more time, it has propagated farther into the shaft, and the backside has bounced off the near wall and created an additional reflection and signal that's going to cross the pile. Further out, it continues across. And then as we continue, the wave eventually reaches and has actually passed the recording point for location B. And it continues, and there are continual residual reflections as we continue through time. And if we look at the recorded signal at location B, we see a first arrival time, The signal goes on and rings, and it's not the simple signal that we had input, because there are reflections all over from the edges and reflections from the back wall and so forth. So in a very simplistic manner, we emit a signal from the transmitter, and we receive the signal sometime later due to the transit time through the concrete at the receiver. As an example, the typical presentation of this data, anytime we have a positive signal, we call it black, and anytime we have a negative signal, we call it white. So we have black, white, black, white, black, white continually across. And at each location, at each depth in the pile, we have black, white, black, white, black, white, and it continues on for a considerable period of time. In this example, we have a shaft that's 16 meters long. 16 meters long. The typical resolution of making a test is every 50 millimeters. It can be every 25 millimeters. For every 50 millimeters for a 16-meter pile, that would generate 320 pulses. So we have a pulse, we have a pulse, we have a pulse, and this is a compilation of the pulses as we go through the pile. The most important part of this waterfall diagram, as we call it, is the left-hand edge. That's the first arrival time. That's really the only important part of such a presentation. And where we have a gap, that would indicate a defect. This particular defect was created by putting sandbags around the reinforcing cage, and here are the tubes. So you see that the path between tubes has been blocked by the defect, and the defect clearly shows up in the waterfall diagram. The testing in the United States of crosshole sonic logging began in 1990 through the sponsorship of our Federal Highway Administration. It's become quite the standard thing to do to check the integrity of drilled shafts. So how do we collect and process the data? Well, we have probes. One's a transmitter and another one is a receiver, that we place in the bottom of access tubes, which are pre-planned and placed in the drilled shaft. We fill the tubes with water to couple the transmitter and receiver into the system. We select a quadrant for the probe. So looking at a top view, we would take these two tubes and put the transmitter in one and the receiver in another. And then we can pull the transmitter and receiver from the bottom to the top, and thereby check at each location along the length of the shaft for the integrity of the pile. We can, of course, once we've concluded this test, we can move the probes into all the other combinations. So for a 4-tube shaft, we have 6 different combinations that we can possibly test. Here you see the operator. We have depth encoders that we know then as the cable pulls across the depth encoder, it records the depth that the probe is in the tubes. He pulls and raises the probes simultaneously. We can have a system with 4 probes at one time. So with one pull, you can get all 6 profiles in one pull. In that case, the probes are both a transmitter and a receiver. And so one would transmit, the other 3 would receive, and then they rotate. So this one could transmit, the other 3 would receive. The next time around, this one would transmit, and the other 3 would receive, etc., going around in squares. So what happens if we have more than 4 tubes? Well, we can test 4 at one time. Then we can move the probes, and test an additional 4, and then we can move the probes again, test again, and in this way, with 3 pulls, instead of 15, because there are 15 paths with 6 tubes, we get done much more quickly. And if we have 8 tubes, we can do the same thing. And with 4 pulls, instead of 28 paths, we can get more or less everything that we need. If you're worried about the ones exactly through the center of the shaft, 2 more pulls would give you all 28 pulls with a few extra recordings. You can also put the encoders out at the access tubes and not worry about a tripod. That's probably less common, but very possible. So in the signal, here we have the signal in the upper left-hand corner. That is, it rings when you excite the probe with a high voltage. It pulses, and this is the received signal, and it is transmitted across. The most important part is, again, the very first arrival time on the left-hand edge of this. That first arrival time we see again in the waterfall diagram of the left edge of the waterfall diagram. And we could numerically pick that off and put that in a presentation so it's a single graph. And here we see the delay in time at the locations where we have white spaces in the waterfall diagram. And that is usually done with some type of an automatic picking mechanism. We call it Edge Finder. That will pick the first arrival time, first arrival time, FAT, we call that FAT. And then that's a signal image processing software. The amplitude of the signal also gives us additional information. And if we integrate the early portion of this, integrate the absolute value, then we call that the energy or relative energy. We can compare it to the strongest signal. And again, we see delays or weaknesses. We have high to low. So we have high values of energy and low values of energy where we have the white spaces. So how do we find a defect in a shaft? We could look at the waterfall diagram. We can look at any individual depth in that. And if we see a good signal strength and an early arrival time, that indicates that we have a good quality concrete. By contrast, if we have a very weak signal and the delayed arrival time, that corresponds to one of these white spaces in the waterfall diagram or a defect. So they're relatively easy to find. This particular shaft was cored, and this is the coring result, and you see that that's not what you want. We had a segregation problem there. Probably caused maybe by a tremie issue in the drilling of that shaft. So if we take a look at the waterfall diagram, we can spot defects by these white spaces, which are relatively obvious. In the processed result, we can spot them by the delay in the signal. This is the arrival time, and we see the arrival time has been delayed at those locations. And we can also see that the energy is reduced at those locations. We can have the computer automatically look for defects with a defect analysis button. So the defects can be automatically found and recorded and placed in a table for report generation. The signal goes generally fastest on a direct line between the two tubes. So that's the fastest arrival that it could possibly be. Due to the presence of aggregate and so forth in the shaft, the signal also can follow curved paths from one tube to another due to reflection and refraction in the concrete itself. Well, what happens if we have a defect that interrupts the direct path? So we no longer have a direct path, and the soil or necking defect there would have a very slow wave speed there. So the fastest wave speed will actually be a curved path. So we would see a first arrival time delay because it's a longer path. And we will also see a greatly reduced signal strength because of the interruption of the direct path and the loss of energy that's going through the actual defect. The Russian study had the opportunity to check defects of 5% and 12% that are located on the direct path between the two tube locations. And in the perfect pile, we see the arrival time as very consistent, very radial. If we have a small defect, we can see that the signal strength has been greatly reduced. The color is markedly smaller here, and you can see a little wave in here which indicates there's going to be a delay in the arrival of the signal. Again, it takes a little bit more time to go around the defect. And the larger the defect, the more prominent that delay is, and the weaker the signal strength is. And if we take a look at the actual arriving signals, for a perfect pile, we have a very strong signal. For the 5% defect, we have a 12 dB decibel loss in signal, and you can see that the signal strength has been greatly reduced. Every 6 decibels means you've cut the signal strength in half. So 12 would be 6 cutting it in half, and another 6 cutting that half in half. So we have only half of a half or a quarter of the signal strength in this particular case. And the larger defect has another 6, so that's half of a quarter or 1/8 of the signal strength in this location. Notice also that the first arrival time is 0.17. For the 5% defect, it's 0.2 milliseconds, which is an 18% increase in the first arrival time. And for the 12% defect, we have an arrival time of 0.22 milliseconds, or a 29% increase in arrival time compared to the actual signal. So if most of the pile is good and intact, good quality concrete, but we see a 29% increase in arrival time, we know that we have a relatively large defect in the system. Now, this defect, if we had had 4 tubes, could have been along the side, and we would have had the same basic effect. So let's take a look at a few case studies. First thing we want to know is, when should we be doing this testing? We installed a shaft in our office several years ago, and then tested it every day. So on day 1, this was the Crosshole sonic logging result. We had actually had 4 different trucks deliver the concrete. So the first truck delivered this lower portion, the second truck, the third truck we purposely put a weak mix in, and then the fourth truck sort of somewhat in between. And so you can see that there's a difference in the quality of the concrete. By day number 2, not so obvious anymore. And we had also installed some purpose-built defects in the shaft, by the way. By days 3 and certainly by day 4, things had stabilized, and after that we had essentially no change for months. The ASTM standard requires that we test, quote unquote, no sooner than 3 to 7 days after casting. And the French standard would require testing only after at least a 7-day wait. Well, here's a test that we had tested at 10 days, and the top portion of the shaft has an obvious problem at still 10 days. One of the suggestions, if we have such an issue, is to test again after a few more days. So at 13 days, the problem had essentially disappeared, and we had a good shaft. These things can happen due to a variety of reasons, particularly if you're using retarding mixes, retarders in the mix, to delay the curing of the concrete. Here's a test where we clearly see a problem in the top 10 feet. This was recorded in the United States, so we have United States units. So we have very bad quality concrete in this upper portion of the shaft. As it turns out, the concrete was placed through water in the top 10 feet because they had a tremie problem, and the shaft was then cored. You can see the poor quality concrete, very soft by comparison. You could chip at it very easily. That shaft was rejected. Here's another case where we clearly see a defect at a certain location, about 11, 12 feet below the pile top. There's the core, a very sandy looking concrete at that location. Again, concrete quality problem. Of course, the same thing can happen at the bottom of the shaft. Clearly, we see a problem down here starting at the 20-meter depth, and it was cored. There's the 20-meter location down to 25 meters, so 20 to 25 meters. Very poor recovery, not a surprise based upon the crosshole sonic logging result. Here's another one. This is a 6-tube shaft, and here we see all the perimeters. We see good quality concrete here, bad quality concrete down at the bottom, indicated by the delay in the signal. We can look across the major diagonals or the minor diagonals, and we still see the same problem in every single profile. The good quality concrete, the core came out very nice. The bad quality concrete came out very almost fluid-like. And in fact, you could stir that and create just a mix. So very, very poor quality concrete. Midshaft anomaly. Here we see it in all 6 profiles of this 4-tube shaft, and it starts at 28 feet depth. There's the 28 feet depth core. The coring indicated solid concrete to 28 feet and then clean sand for a considerable period of time there. All 6 profiles indicated that same defect. And if you look closely, anything that had a tube 2, so 1, 2, 2, 3, and 2, 4, all had some type of a minor defect located at about the 15-foot location below the pile top. So after we find these, how do we interpret the flaws and defects? What do we do with that data? Well, there was a 3-year study by a Deep Foundation Institute task force headed by Anna Saluntu. I was a participant. You can get a copy of this paper on the website, and you can just click and get a hold of that. We came up with a recommendation for classifying these anomalies based upon both first arrival time delays as well as the relative energy reductions. So if we have a first arrival time delay that's less than 15% and the relative energy reduction is less than 9 decibels, we call that a Class A. In other words, that's basically good quality concrete. Between 15 and 30%, this yellow zone, or if the energy reduction is more than 9 decibels, we call that maybe some questionable type concrete, and we'll talk about what to do about that in just a second. If the first arrival time delay is 30% or more, or a very large amount of energy reduction, 12 dB or more, that's highly questionable and probably indicates some type of a defect in the shaft. And we're going to classify each anomaly. So we might have, say, 4 different anomalies in one profile, and each anomaly would get a rating of A, B, or C. We have chosen to recommend looking at the first arrival time increase, or the delay in arrival time, as our standard. And 30% arrival time delay is only a 23% velocity decrease. If you take the spacing and divide by the arrival time, you can get an estimated velocity or computed velocity. But note that a 30% change from a value of 1 either is 1.7 or 0.7 or 1.3. And 0.7 does not equal 1 over 1.3. 1 over 1.3 is 0.77, and the complements of 0.07 are 30%. The complements of 0.77 are 23%. So we again recommend looking at the first arrival time delay rather than looking at the velocity decrease. So what do we do if we have a category B? These are the questionable ones. Well, first of all, we want to rule out any possibility of debonding, and I'll talk about debonding in just a minute. We can retest after a longer wait period. I already showed you an example of that. We can do a tomography analysis, which is a computer simulation of looking through the curve and trying to estimate how big the problem might be. And we should always consider the depth and location and the number of affected profiles. Let's take an example. Let's say we have a 6-tube shaft, we have 15 profiles, and we have 1 Class B result at mid-depth. Well, first of all, the entire shaft is not classified as Class B. Each anomaly is classified as a Class B, but the entire shaft we have to say is not in and of itself questionable. We want to use some judgment. So in judgment, the first thing we're going to do is consider the depth and location and the number of affected profiles. If I have only 1 profile out of 15 and the location is far enough from the pile top, I probably don't care. The shaft will probably perform in service very well. The other thing to consider is just because it's Class B, it might be over here very close to a Class A situation, and therefore this one location, maybe I don't care. It's so close, it's within a margin of error. The 15% is a bit arbitrary anyway. I'm probably going to accept that shaft. On the other hand, if I have several of these Class Bs and they're all at the same depth, and they're on the high side of the B, so it's, let's say, 29%, well, that's almost a Class C. That's probably something that I'm very concerned about and would investigate even further. What happens if I have a Class C, which are the really questionable ones? Well, I can still rule out the same things in Class B. If the defect or potential defect is located very near the ground surface, we can excavate the shaft, dig down 1 meter or 2 and look at it. If it's at a deeper location, we can do some core drilling. If we core a couple locations, we could hydrofracture the bad quality concrete that we find, and then pressure grout the shaft to try to restore the integrity. We could try other tests. We could try the low strain integrity testing. That's relatively inexpensive to do, and particularly if the defect is located fairly close to the top of the pile, that could be a definitive confirmation of a problem. You could do a high strain pile driving analyzer test, PDA, and that has been also used successfully to verify that the shaft is either okay or has a serious defect. Of course, you're always left with the possibility of you have to repair something or replace the shaft in the structure. Again, it's very, very important to consider the location of these anomalies and the number of affected profiles, particularly if the anomalies all occur at the same depth. So debonding. What is debonding? That is a weakening of the bond between the tube and the concrete. The coefficient of thermal expansion for concrete and steel is practically the same. And so steel bonds very well to concrete. We put rebars in all the time for strengthening the concrete. On the other hand, if we use plastic tubes, PVC plastic tubes, that coefficient of expansion is more than 4 times larger. So during the curing process, when the temperature is very warm in the concrete, this expands more than the concrete does. And when the concrete cools and the PVC tube cools, the concrete will pull away from the plastic tube and create a gap. Generally, we find debonding always relatively near the top of the shaft. For some reason, the deeper locations don't seem to have debonding issues. To minimize or eliminate the problem, use steel access tubes because of the good agreement in thermal expansion coefficients. And good practice always fills the tubes with water as soon as possible after the concrete has been installed. And to mitigate the problem, we can flood the top of the shaft with water. Let's give an example of that. Here we have a test. Basically, the shaft looks good up until the top 5 feet of the shaft, where we have a significant loss of signal strength in all of the profiles. And I've just showed 2 here, but they all show the basic same problem. If we flood the top of the shaft, we build a little dam around the outside, pour water on there, let it sit for a while, come back and retest. So after 45 minutes of waiting time, it allows the water to seep down the gap between the tube and the concrete, and it has restored the path so that the signal can cross, and we see good quality concrete again in all of the profiles. So it doesn't take long, and it's a relatively simple thing to do, and it eliminates any confusion or uncertainty about the debonding issue. Debonding should never be in a report. You can always verify whether it is or is not an issue. Here's a case where they use PVC tubes, and the testing was done 8 days after the installation of concrete, and you see just sort of a mess. Lots of questions and concern in this shaft. It's a relatively short shaft. It's only 5.5 meters long. Well, the tubes were removed. Relatively simple to do that. They used dry ice to shrink the tubes and then pull them out. And then they retested at 11 days, and you can see that the shaft looks perfect. So the recommendation is to always use steel tubes and avoid plastic or PVC tubes. Another issue or problem that can occur in crosshole sonic logging testing is observed in this particular profile. We had a relatively poor mix, and in this particular case, we had a permanent casing in the shaft, and you can see that the location that corresponds to the permanent casing is again relatively weak, and it's caused by the flow of water. The water cannot escape laterally, so it has to escape vertically, and it creates bleed water channels. You can see little pinholes all over the place. That interrupts the flow of the signal from one tube to the other, and so while it's an anomaly, the actual strength of the concrete is actually fairly good. In this particular case, purposely a styrofoam shell was put on the outside of the access tubes for testing, and clearly it's not blocking the path between the tubes. And in the waterfall diagram and the first arrival times or the energy, we see no effective change in the signal. We can't detect a defect that's outside the cage. And that is a significant limitation of the crosshole sonic logging method. We can only test the concrete inside the reinforcing cage. Just as a side note, sometimes we create our own problems when we're drilling shafts. In this particular case, we have overlapping bars over a section of the shaft. And if the bars are that close, we're going to have a hard time getting the concrete that's pumped inside the cage to flow outside the cage. And we likely could have a issue in the concrete cover, the concrete outside of the cage. Sometimes we have double cages that are installed for a variety of reasons. One reason being we could have a shaft that's two different diameters, larger at the top and smaller at the bottom. And when we do that, we can see that the path might be interrupted by some of these inside cages, and therefore we might see some shadow effects as a result of the extra reinforcing there. Or if we have the access tubes outside of the cage for some reason, and again an inner cage, while these profiles would look good, a profile that goes across this cage would again be interrupted by the steel reinforcing, and might have a signature or an anomaly appearance. Usually the access tubes are tied to the inside, like is shown here, the inside of the outer reinforcing cage. So tomography. What is tomography? Tomography is an way to evaluate whether we have a local defect. Let's say we have a local defect, and we do our 6 pulls in this particular case. We can see that this defect is going to cause a problem across the center and across this perimeter set of tubes, but the other tubes all look okay. There's no path interruption. The signal strength is good. So we've already determined that the defect is in this quadrant of the shaft. Of course, if we have more tubes, then we have a better definition. So the more tubes that you have, the easier it is to locate where the defect might be. If we have a shaft where we have a defect in every single profile at the same depth, we don't have to do a tomography analysis. We know we have a full layer defect. Similarly, if the entire shaft looks good, again, no reason to do a tomography analysis. It's only when some profiles have a defect showing and other profiles at the same depth look perfect that a tomography analysis to determine the size of a defect might be useful. So here's a case where we installed purposely a half-moon styrofoam shelf in the shaft. And we can see from the tomography analysis basically the signature of that half-moon styrofoam shell. In our software, we have all the profiles listed. We simply say export to tomography. It shows some examples. It cleans up some of the data to make it more uniform. And then we export, and out comes a solution. And we can look at various slices. So at particular depths, this is at this particular depth. We also installed extra defects at other locations, which were similarly found. So in summary, the crosshole sonic logging has various advantages. It's not limited by the length to diameter ratio. It does a very good job checking the concrete quality inside the cage by depth and by quadrant. The installed tubes inspire better construction in the first place. Even if they're not tested, the possibility of being tested will inspire the contractor to be more careful during the construction process. And tomography is available. Limitations and disadvantages, well, we have to wait for the concrete to cure before we can do the testing. And the typical time is somewhere between 3 and 7 days. And if we see a problem, then we might have to retest after a few more days. So there can be a considerable delay in time to the construction process to verify that the quality is good. Of course, we want to verify the quality is good because once we've built a structure on top, if the foundation has a problem and fails, then we're going to have to tear the whole thing down. So it is important to verify the quality of the foundation. Access tubes are required. We prefer steel access tubes so that we do not have any debonding issues. And in the United States, most of the tubes are then later filled with grout after the test is completed. So that's an additional cost, an additional expense to the project. You cannot see outside the cage. That is the biggest limitation. So really, it's a relatively limited cross-section that is tested. Certainly a good idea to do some testing. Unfortunately, very small defects near a tube can appear to be very large. You'll see a vastly reduced signal strength. It can't bend sharply around a defect located there. In fact, if the defect surrounds the tube, every profile, like in that one example for tube 2, would show a potential defect. Debonding and bleeding are issues that can create confusion on the job site. An anomaly is spotted. We say, hey, we have a problem. And if debonding is not ruled out by flooding the top of the shaft, then there could be some coring done or the bleeding issues. And any delay in the project, of course, time is money. So I thank you for your attention, and if you have questions, you can contact me through my email address, engineer@pile.com. There's also 2 other experts who are receiving that in case I happen to be unavailable at the time. And there's a considerable amount of information on our website, pile.com. There's a reference library of many papers. So we thank Geotecnia for inviting us to present this lecture, and happy testing.